Okay, so we're taking a look at section 7.2 today, and just to give you a quick overview about what this section is going to be about, first we want to be able to identify what a basic feasible solution will look like in this transportation tableau. We know what it looks like for a linear program, but we'd like to be able to identify it with using our new array notation for the tableau. And we're also going to be looking at some methods for computing an initial basic feasible solution, and those are three. Northwest corner rule is the first one, pretty straightforward. Minimum cost rule will also be fairly straightforward. Vogel's method, also known as VAM, is a little bit more complicated. Typically, the way this works, it's not always true, but typically the more work you do to get that initial BFS, you hope the better your initial BFS is. And so that's why we have all these different rules. And actually we'll be looking at this second piece in the next video. So for this video we're going to focus on a little bit of theory to try to figure out how to identify a basic feasible solution for the transportation tableau. Good, so just to start things off, let's take a look at an example that we'll use. You can see we have two warehouses, three customers. We have some demands here, 5 and 2, or sorry, some supplies, 5 and 2, and then we have some demands from our customers, 2, 3, 2. We have some costs, and we have 6 decision variables, right? And so this is a nice, what is that called? Where you have the same number summing here as you do here. Balanced, that's right, it's a balanced transportation problem. Good. So our original LP then has 6, these are our 6 decision variables. I'm using Y because this is a minimization problem, right? We're minimizing our cost. And then what are our constraints? The constraints are you have 2 row sums and then 3 column sums, right? And because this is a balanced transportation problem, we can actually make these equalities instead of inequalities. So here's our first 2. These are our 2 row sums, and then our 3 column sums come in next. Good. And so from this we could write down our dual. Oh, by the way, the Yij are all positive. From this we can write down our dual, and I'm going to use some special variables for the dual because these will be coming up later in another section. So Ui I'm going to be defining to be the dual variables just for the supply, and Vj will be the variables just for the demand. So we'll have U1 and U2 kind of representing the first 2 constraints, and then V1, V2, and V3 will be the dual variables for the 3 demands, right? Okay, so using those variables then, we can kind of see what our first constraint is going to be, right? U1 plus V1 is going to be less than or equal to 3 because this is actually the dual, right, of the dual. And so normal for that problem would be less than or equal to. Then we have V1 plus V2, or sorry, U1 plus V2 less than or equal to 7, and so on. Okay, we'll go ahead and write these out. Very good. This kind of got cut off a little bit. This is saying where Ui and Vj are unrestricted variables. Why are they unrestricted variables? Because these are equality, right? Good. And so here's our summation. This is now our max problem. All right. And so it's good to keep these 2 problems in mind because these are the underlying linear programs that we're trying to solve. Okay, good. In general, we can write down the dual this way. Well, we won't write it this way very often, but it's good to just think about it this way. It's the max, and these are the supplies, and these are the demands. So the supply values times our u's plus our demands times our v's. That's our objective function. And then you could write this a couple of different ways, right? Our book actually writes this in reverse, I believe, although I like to use it this way instead because it matches what we're going to be looking for as a goal later on. Okay, so um, we're going to look at this again later, but this is kind of just the setup in our notation for the dual. So if you see some u's and v's, you might remember those are the variables that we're using for the dual. Okay, so getting back to our initial question, we were asking what does a basic feasible solution look like for our original problem. Okay, um, later we'll be talking about how to compute the solution to the dual for that. But for now, let's go back to the basic feasible solution. So suppose I have AX equal B, where A is a matrix that is R by C with rank R. This is kind of the setup that we had initially in chapter 6, wasn't it? Where we were solving our system of equations. C is usually bigger than R, so that A is a wide matrix, right? Then in that case, how do we find a basic solution? Well, we set the extra variables. We select how many variables? C minus R variables to be our non-basic variables. We set those to 0, so you could actually just remove those columns from the matrix from this system over here. That would give you an R by R matrix A that is invertible, and so then you could solve this for X, and that gives you your basic solution. So what is the basic solution? It's where you set C minus R variables equal to 0 and solve for the other R variables. Okay. Now, what this depended on was that this matrix A was actually full rank, and we're actually going to run into a problem with that. So what is the matrix A from our transportation tableau? In this particular example, this was our matrix A, right? And so in general, you would, if you have like M warehouses and N customers, the matrix would be M plus N by the number of decision variables, which is M times N. In this case, that's 5 by 6. And the question is this array actually rank 5? Well, in fact, it's not, and that's going to create a little bit of a problem for us later on. A is not full rank. In fact, if you sum the first 2 rows, what do you get? If you sum the first 2 rows, you get 1, 1, 1, 1, 1, 1, and then a 7. What happens if you sum the last 3 rows? You get 1, 1, 1, 1, 1, 1, 7. Uh-oh. The sum of the first 2 rows is equal to the sum of the last 3 rows. That means that those rows are linearly dependent. Dun, dun, dun. So that's going to be a little bit of a problem. Okay, so actually the matrix is rank 4, although we didn't prove that. We just showed that it was less than 5, right? So the matrix is going to be 1 less rank. So this is going to create a little bit of a problem for us, although not too much. We're just going to have to keep that in mind. The transportation tableau has a little bit smaller rank matrix. Okay, so let's get back to the main problem then with this following 3 lemmas. Is the transportation problem always feasible? The answer will be yes, as long as the transportation problem is balanced. Number 2, the number of variables required is equal to the rank. We just showed that the rank was less than M plus N. So how much less is the question? And if we have a linear dependence in the variables, how do we know that we've chosen the correct variables? We want our variables to be linearly independent. Okay, so I have 3 lemmas that solve those questions. So let's get to them. Lemma 1, feasibility. Excuse me, if I have a balanced transportation problem, then I have a feasible solution, and that feasible solution is found by taking our decision variables to be SI times DJ, the ice supply, times the jth demand, divided by this common number T, the common number being the sum of the supplies or the sum of the demand, which should be the same thing. So in this particular case, let's see, this 15, for example, 15 over 7. The 7K is the sum of these, 5 plus 2, or 3 plus 2 plus 2, because it's balanced. And then the 15 on top comes from 3 times 5, right? 3 times 5 is 15. This 6 comes from the 3 times 2. Okay, and so this is a nice feasible solution, but it is not basic. It's not basic because we don't have any zeros in there. All right. So given the matrix A, which has these dimensions, the rank of A is exactly n plus n minus 1. We're just going to state this without proof. It's hard to prove. So in this example, we have a 2 by 3, and so our matrix is 5 by 6. The matrix A is 5 by 6, right? And so the A has rank 4. And so that means the number of decision variables that I need to make the solution basic is 4, right? I need to assign 4 variables um, to be basic. Okay, and now remember there's a linear dependence among the variables. So for example, oops, I'm not getting my example yet. Sorry about that, I'm running out of time. A set of variables is going to be independent if they form no loop in the transportation tableau. I gave away my big headline here. This is kind of an odd thing because we talked about loops before, and it turns out that if you have a loop in your variables, there is a linear dependence among them. So when you're checking your variables to see if they're linearly independent, you want to make sure you have no loops. Okay, so that's my summary now. A solution is a basic solution if it has m plus n minus 1 assigned variables, and those variables form no loops. It is degenerate if one of those assigned variables is 0. Okay, so in this case, for example, I don't want to make these my 4 basic variables, right? Because I have a loop, and those 4 variables would be linearly dependent. Okay, so rather I might use something like this. These variables do not form a loop, but of course I don't have enough variables, right? I do have enough variables to make the array a solution. This is a solution, but to be a basic solution I need one more variable to be assigned. I just want to assign a 0 somewhere so that I don't have a loop. So I could put it here, I could put it here. This is a good one, and so now I have my 4 variables that form my basic solution. Okay, good. I'm out of time, so I will see you in the next video.